We will continue with our 8th lecture. This is the first time in this course I am going to introduce the notion of Laplace transforms. I will explain what Laplace transforms are and why are they useful in control. Laplace transform basically from a control viewpoint can be used to solve the same state space equation that I showed you in the last class. So, in the last class we saw how we can solve that state space equation in time domain. The same equation can be solved in what is called the Laplace domain, and there are certain advantages to working with the Laplace domain, which I will explain as we go through this lecture. I also want to point out that I am going to teach Laplace transforms purely from the viewpoint of its use in control. So, I am going to take certain liberties in definitions and so on, so that it is easily understandable for an undergraduate student who is looking at this for the first time. Let us start by defining what a Laplace transform is. When we define this Laplace transform, you will see why this definition is useful. So, mathematically I will define it, and then I will actually motivate why we might use something like this in solving differential equations, and as a result use that in control. So, a one-sided Laplace transform of any function f of t is defined as this. Laplace of f of t is f of s. It is an integral between 0 to infinity f of t e power minus st dt as shown here. Now, the main thing that I want you to notice here is when we take a function which is in time domain and take a Laplace transform of that time domain function, then it goes into the Laplace domain and it becomes a function of s, which is not yet defined for us. So, the standard notation is if you define a function in time domain using lowercase alphabets, in the Laplace domain you change the lowercase alphabet to an uppercase alphabet. So, small f to capital F, and this variable is t and here the variable is s. And let us just make sure that the right hand side is also in variable s. So, since we are integrating from 0 to infinity f of t e power minus st dt, the t will get integrated out and what will remain will just be a function of s. Now, what is this s? We just simply say for now that s is a complex variable which is of this form. We will rarely, if ever, try to worry about what s really is in terms of sigma and omega and so on. We will use this complex variable s in terms of its solution, what we are going to call as the poles and zeros of a transfer function, and then all the judgment we need to make in terms of control can simply be made based on the solutions to this s when we solve an equation in s. So, which we will see later. So, for now all I want you to understand is that you are going to get a function of s, and s is a complex variable, that is all I am going to say, and the complex variable can take many values just like how time can take many values, but we are not going to yet define what values it will take and what is the implications of those and so on. So, you might ask why do all of this. So, the simplest explanation from say solving equations and a control viewpoint is the following. We will see that if you have a model in time domain which is an ordinary differential equation, which is what a state space model is. Remember, we talked about the tank model and then showed how that is going to be simple differential equation, ordinary differential equation. Now, we showed that you can actually solve that ODE using integrating factor. Actually, Laplace transform will also look very similar to the integrating factor, but we can convert that equation, which is an ordinary differential equation, through the application of Laplace transform into equations in the Laplace domain. Now, why would someone want to do that? The reason is you will see as we do this that the ordinary differential equations in the time domain become algebraic equations in the Laplace domain. So, it is much easier to solve large number of algebraic equations than time ODEs. So, it makes us solve these equations easier. And not only it allows us to solve it easier, it also gives us an interpretability for the solution. As you get good at this, we can bring in notions of frequency, frequency of signal and so on. So, we will get a more intuitive feel for what the results are when we think about these aspects in the frequency domain or the Laplace domain, and we will see this later. So, keep looking out for how this ODE becomes an algebraic equation as we go through this Laplace transforms. Now, once you convert a ODE to a Laplace domain, of course, you got algebraic equations. and you could solve these algebraic equations, but then the question is the solutions will also be in terms of s, but really all the physical interpretation happens in time domain. So, I am going to ask, let us say if I increase the flow rate inlet to the tank, how is the height going to vary as a function of time? I am not asking how the height is going to vary as a function of s, which is an abstract concept. So, while it is useful to convert these equations into the Laplace domain, get algebraic equations, one then has to do what is called this inverse Laplace transform and then convert the solution back to time domain. Okay. So, the way this thing works is you have the variables, differential equations, convert them into Laplace domain and get the solution in Laplace domain, and then the solution you convert back to time domain using inverse Laplace transform. So, this is the format in which we are going to use Laplace transform. So, let us go back look at the state space model, which is x dot equal to ax plus b, y equal to cx. Remember, if you were thinking about this for the tank example, the equivalent model was h dot equal to minus 1 by tau h plus k by tau fi, right. This was a model equation that we saw, where minus 1 by tau will be a, k by tau will be b and so on. So, this equation again I am just trying to point out, though we have done this many times, I just want you to understand that none of this is completely abstract. All of this is rooted in reality in terms of the process, equations and the equipment and so on. So, basically somehow our physical process has been made into system of equations like this. Now, I want to solve these set of equations. So, just like how I did my integrating factor when we were solving the time domain equations, let us assume that I am multiplying both sides by what the term that I am going to use, which is e power minus st, which this is something I can do since I am multiplying the equations on both sides. So, I will have this equation to read as e power minus st x dot equals a x e power minus st plus b u e power minus st. Keep in mind, for not cluttering the slides, we have just written x, but really x is a function of time x of t and u is also a function of time u of t. So, this is actually x is a function of time, u is a function of time. Now, there is nothing to stop us from integrating this equation from 0 to infinity. Now, I go ahead and integrate this equation 0 to infinity e power minus st x dot dt equal to a 0 to infinity x e power minus st dt plus b 0 to infinity u e power minus st dt. So, what till now we have done is we have taken these equations and simply multiplied it by some term which I am allowed to do, and simply integrated, which I am allowed to do also. Now, something interesting happens. If you notice this here, you will see that is exactly the definition of Laplace transform. So, Laplace of x of t, if I write it like this, Laplace of x of t, remember I told you that x is a function of time, will be equal to integral 0 to infinity x of t e power minus st dt. Okay. So, that is what this is here, and similarly this from the same definition will become u of s. So, this equation now turns out to be 0 to infinity e power minus st x dot dt. We do not know what to do with this yet, but on the right hand side things have simplified quite nicely. I have a times x of s plus b times u of s. So, now let us take a careful look at what we had on the left hand side of the slide that I showed just now. So, we had on the right hand side we had got variables defined in terms of Laplace transform. So, there is no t term in the right hand side, but if you look at the left hand side, I still have this 0 to t e power minus st x dot dt. Clearly this is going to be only a function of time, because x dot of t is also going to be a function of time, and once we integrate time out, then we will have only a function of s, but still we do not know what that is. So, to simplify this and get it into the Laplace domain with only s variable there, what we are going to do is we are going to use a rule that we are all very comfortable with. We have been using this for years starting from high school, which is using the integration by parts rule, which says if you have integral w dv, you can write that as wv minus integral v dw. So, the key thing here is when I have something like this, I have to define what w is and what dv is. So, if I were to define e power minus st as w and x dot dt, which is remaining as dv, then when I do dw, which is I have to differentiate e power minus st, then I will get minus at s e power minus st dt, and when I integrate x dot dt, then I will get v equal to x. So, this is quite straightforward. So, I can write this 0 to infinity e power minus st x dot dt as w v. So, we had w defined as e power minus st, and after integration we got v as x. So, x e power minus st 0 to infinity minus 0 to infinity v dw, v is x, dw is s e power minus st dt. So, we have got this here. So, now if you look at this term, so there is a minus minus, so it becomes a plus. So, I have integral 0 to infinity x s e power minus st dt. Since the integration is with respect to dt, I can bring the s out. So, I have s 0 to infinity x e power minus st dt, and if I come to this term right here, when I substitute infinity, if x of infinity is bounded and e power minus st is 0 when t tends to infinity, then the first term goes to 0. And when you substitute 0 here, then this is x evaluated at 0 times e power minus s into 0, which is e power 0, e power 0 is 1. So, this will simply lead to this. I get a minus here because I first evaluated the top limit infinity and then I evaluated the bottom limit. So, this is what happens, and if you assume that these equations were actually written in the deviation variable form, then you know at initial condition is 0. So, we can assume that this is 0. So, I am only left with this, but now notice what has happened. If you look at this inside this, okay, x e power minus st dt integral 0 to infinity, you will notice that is the definition of the Laplace transform for x t. Okay. So, this I can replace by x of s. So, this with all of these conditions and the initial value being 0 because it is a deviation variable will turn out to be s x of x s x. So, if I substitute that into the left hand side of the equation that we saw before, then I have an equation of the form s x x equal to a x s plus b u s. Now, notice the difference between this equation and the equation that we had in the time domain. Time domain we had a differential equation. Now, we are solving for x in that as a function of u time, and I had to solve a differential equation. But now, if I restrict my interest to simply solving for x in the Laplace domain as a function of u, then this is a very simple algebraic equation. I can take this term to this side, I will get s minus a x of s is b u of s, then x of s is b by s minus a u of s. So, this basically already automatically solves this problem for me, and it has given me the solution x of s in terms of u of s. Now, the other equation is y equal to c x, which is anyway an algebraic equation. So, if you do Laplace transform on both sides, you will get y of s equal to c x of s. So, y of s is c, x of s is b by s minus a u of s. So, I get this transfer function. Now, if you look at only the relationship between the input and output, then this is the equation that we are interested in, and then we see that the output in the Laplace domain, which is y of s, is related to the input in the Laplace domain, which is u of s, by this equation, and I could call this g of s as cb by s minus a. Now, this is the first time we are going to introduce this idea. So, this g of s is what is called a transfer function, and the transfer function is modeled in the Laplace domain. Now, though we have come to this equation, which is ubiquitous in all of control, generally people start with this transfer function model. I hope you see the route through which we have come here, and there is no magic to this. This comes out of your standard state space equation, and the standard state space equation comes out of the physics of the problem. So, I already told you that this B and A for the tank example actually can be calculated in terms of physical variables and parameters in the system. For example, the area of the tank, the resistance valve, and so on. So, what we have done really is taken a physical system and then modeled it with variables and parameters, and those parameters becomes coefficients in a state space model of the form x dot equal to ax plus bu, y equal to cx. And that state space model can be translated into a transfer function model, which is of this form here, with the coefficients in the state space model, which are actually related to the physical coefficients. So, these are physical coefficients, and that is how they come into a transfer function form. So, you see that once you work in the Laplace domain, you get one definite advantage, which is that instead of solving differential equations, you are going to solve algebraic equations. So, when you have multiple equations, you want to make judgments about these, it is easier to look at an algebraic solution and get an understanding. So, just like how there is a y of t which can be converted to Laplace domain and a u of t that can be converted to Laplace domain u of s. Clearly, for g of s also there should be a g of t, right, because it is a transfer function. So, every function has, if it is a Laplace function, then there will be an equivalent time domain function. Now, we will see later that if your function is of this form, then that would have come from a g of t of this form Cb e power at, and this Cb e power at is called the impulse response model of the system, and we will see why this is called the impulse response model of the system as we go forward in this course. So, let us summarize by talking about how one would use Laplace transforms. The first thing is I take a time domain set of equations, okay, which are going to be in xt, ut, yt, and then I do a Laplace transform. Then I get equations in terms of xs, ys and us. Once I have this equation, so here I have to get time domain solution, which is an ODE, solving an ODE. Here the solution becomes a solution to an algebraic equation. Okay, so we know, for example, if I want x of s, I know, just to recap, x of s is 0 to infinity e power minus st x dt, right. So, I know how to go from x to x of s, and similarly y of s is 0 to infinity e power minus st y dt, and u of s is 0 to infinity e power minus st u dt, and so on. So, I know how to go from here to here. But I made this point that, okay, you did all of this, great, and you got the solution, and so you tell someone y of s is this. So, what does it mean, right? I have not yet defined what s is exactly. I am looking for an answer to a very specific question, which is, if I increase my inlet flow rate, how would my height vary? And if you say height will vary in the Laplace domain this way, it is not very useful. So, somehow we have to do an inverse Laplace transform to go back into the actual solutions of xt, yt and ut, otherwise it is not useful. So, this part only converts the equations with these variables from ODE to algebraic equations, and once you write the solutions, which is explicitly writing y of s in terms of u of s and so on, I still need to be able to write the solution explicitly in terms of xt, yt, ut, and that is done using what is called an inverse Laplace transform. Now, it is easy to write this Laplace transform, whereas the inverse Laplace transform is a more complicated expression, which is a complex integral that you have to do. Now, that is quite difficult to solve compared to the forward transform, which is the Laplace transform. So, you might ask, if it is difficult to solve the inverse Laplace transform problem, so what is the point in doing all of this? The point in doing all of this is the following. In almost all cases, I am going to show you that we are never going to do this integral itself every time we encounter a problem, and as a result we are not going to do this integral either. So, the key idea that you want to remember as to why Laplace transforms are very useful for engineers who do not know complex analysis, residue theorem and so on, is the fact that I can simply look at tables and then do all of this without actually doing the integration. So, all the hard work in some sense has already been done. So, the way you use Laplace transform is the following. So, you will have a table which we will see in the next lecture. So, here you will have different functions f of t, and here you will have the corresponding Laplace transform for those functions already worked out. So, if you are looking for Laplace transform, what you do is you go from the left side of the table to the right side of the table. First you look at what function you want a Laplace transform for, and then look for that function in this column, and then you go to the right and then pick the corresponding Laplace transform. Now, if you are interested in the inverse Laplace transform, if I have done this right, then the inverse Laplace transform is very simple. What I do is I go and look for whatever I want to invert in this, and then say, okay, I find it here, so I go in this direction and I get the corresponding time domain function. So because of this lookup table where I can go from one side to another side, and since this has been worked out for a large number of problems, and in fact I will show you later through this idea of partial fractions, you can really use only one or two of these entries to do a wide variety of problems. Then Laplace transforms become very, very useful. If you have to actually do the integration and then compute the inverse Laplace transform, it's much more complicated, and that's something we usually do not do. Okay, so I hope this lecture has given you a good idea about Laplace transforms, how the Laplace transform converts ordinary differential equations into algebraic equations, and how once you have these algebraic equations you can solve for the variables of interest, which will leave the variables of interest still in the Laplace domain. Then what you do is you do this inverse Laplace transform and then get back expressions for these variables in the time domain. So that basically completes the whole cycle of solving and interpreting the solution using Laplace transforms. So what I will do in my next lecture is I will take some concrete examples of problems and show you how all of this works with numbers and so on, so you get more comfortable with Laplace transforms. And once that is done and I give you some general ideas about partial fractions and so on, then you will be well equipped to look at these kinds of equations and see how to work with them. I will see you next lecture. Thanks.